To begin this course, for anyone who hasn't taken this before, this is probably your first introduction to fluids. And up until now, you might have been doing some or taking some courses in mechanics or dynamics, and where that's looking mostly at solid or rigid bodies. In fluids, we have a bit of a different material, and the biggest difference between that material is that fluids just cannot withstand a shear stress. So if we were to describe the mechanical behaviors of a solid, we can have static deflection. We can deform that solid. It will deform elastically and plastically. If we deform it more, it'll fracture. Lots of different properties of solids. When we get to a liquid, the atoms are a little bit free-flowing, much more so than solids. They aren't as loosely packed as gases, so they still sort of take some sort of shape, and they would fill whatever container you put them in. Gases, the atoms are, compared to solids and liquids, much further apart, and they have a very different behavior. Some similar to liquids, and then some liquid behaviors more similar to gas, some more similar to a solid. So we're going to be basically giving particular attention to developing some useful forms of linear momentum and energy equations to study some fundamental and practical problems of fluid mechanics for engineering. And then hopefully the labs towards the end of the course will sort of tie in a lot of this material into a real world application, albeit it is just a lab, but it'll be pretty representative of what you might see down the road if you pursue a career that involves fluid mechanics. So today, or just this section for the first half of the course, we'll just go in, we'll cover some significant applications of fluid mechanics, so maybe some motivation, why bother studying this stuff. We'll talk about the concept of a fluid, what is a fluid, classifications of different kinds of fluids, and then we'll introduce lastly fluid as a concept of a continuum. So fluid mechanics in the 21st century has come a long way from when it was first introduced or studied or even thought of. It's used in a wide variety of applications, and it is sometimes thought of as out of fashion or old school or not as interesting as other fields. Maybe quantum mechanics or computing is now much more interesting, but fluid mechanics is still right at the forefront of a lot of engineering design problems and engineering problems. Fluids can also be seen sometimes as quite difficult. There's a lot of complex equations involved in fluid dynamics, fluid mechanics, but if we can try to give a good understanding of some of the basic concepts, it becomes a lot less scary as we go through it. In the past, there was also some paradoxes that were hypothesized or thought of with fluids, and that came to understanding of how the world works, how matter interacts with each other, and through research and science and a lot more recently due to computational methods, we've been able to really push the boundaries of knowledge of fluid dynamics, fluid mechanics, and what we can do predicting fluid behavior. And this is permeating to all kinds of different fields. The most obvious one for an application in fluid mechanics would be aviation industry. One application that I thought was kind of interesting, one of my friends, they would talk about how you have timing intervals when you have aircraft landing and taking off, and one of the reasons for this is because of a fluid effect that happens at the wingtip of an aircraft. So when aircraft is flying and generating lift right during takeoff or right during landing, it can generate, especially these large jumbo jets, can generate really significant airflows in the form of vortices. And these vortices can significantly affect the flight behavior or control of any vehicle, for example, another plane flying through it. So when you have aircraft taking off at an airport, for example, or you're crossing the wake of another aircraft, you have to really consider how much time has passed to allow these vortices to dissipate. If these vortices are not dissipating enough, you might not be able to, for example, generate enough lift by the end of the runway and actually take off. So there is a time constraint. You cannot have aircraft one landing after the other. And this is one of the main reasons why, is because of this aerodynamic effect, which is vortices. Another kind of interesting application, before coming here to Ottawa, I was working developing additive manufacturing technology in the marine industry. And one of the interesting things for marine is propeller design. And this is both for commercial merchant ships, because if you have a more efficient prop, then you're going to burn less fuel transporting goods, which is going to save you money, which is important to companies. And then also in defense, there's similar thing at the end of a propeller blade. If you think of it like a wingtip, a vortice is formed, and the pressure, properties of the pressure around that wingtip vortice can actually cause something called cavitation, which is kind of what you see in the top right-hand corner here. Cavitation is just basically water vapor expanding, and then at some distance away it collapses, and that makes a lot of noise. So if you have like a stealth submarine or other kind of military vessels, you don't want them to be able to be detected easily through things like sonar. You want to reduce the amount of noise that these things create while also maximizing how fast they can travel. So a lot of effort goes into prop design to try and have low speed props to prevent cavitation, but maximize that efficiency at higher speeds. Another application, automotive. This is maybe a little less obvious, especially if you look at Tesla truck. Sometimes some automakers don't really consider aerodynamics too much. There's a lot of innovation and work done in automotive to try and improve the aerodynamic efficiency of vehicles, and especially on highway driving, that seems to be one of the largest contributors to reducing your fuel economy, is by making your vehicle more aerodynamic. So you can reduce the drag, you can increase your fuel economy. At the other extreme, in motorsports, aerodynamics basically determines everything, especially at the extreme like Indy racing, Formula One racing. Tons and tons of money and research is poured into aerodynamic development for these really high-end performance vehicles. And an F1 car has so much down generated just from the aerodynamics that it can actually drive upside down and still maintain grip and not fall. There's that much downforce that it doesn't actually need to drive on an upright road surface. Something that's gaining more and more traction as we improve our understanding of medicine, anatomy, physiology, and then just our technology, our ability to produce materials that are biocompatible and make technologies a lot smaller. And with computational methods being able to simulate very, very difficult and complex systems, is fluid mechanics entering the biomedical field. So this is just some examples down here of maybe a computational fluid dynamic simulation of blood flow during an artery or vein, and maybe we want to design a device that's going to mimic this behavior that could be used as an implant for maybe someone who has some condition where they can no longer, they need to have some assistance pumping their blood, for example, or transporting blood. Or maybe even filtering blood. That's just one case where fluid mechanics could be used in biomedical. I think a topic that isn't really thought of too much, but is seeing a lot of attention maybe behind the scenes because it is so competitive. They don't really want to share the work that's being done, but sports and athletics also has a lot of research and innovation done with trying to improve how fast we can go, how high we can jump, how fast we can swim, basically make faster, stronger. And a lot of times the easiest way to do that along with training, is actually just to design equipment or change our techniques that allow us to be more aerodynamic, more hydrodynamic, or make use of the fluid medium that we are moving through. So a great example is swimming. You have your technique is hugely important to how fast you can go, and also your body build and how you swim. Another one that's quite obvious is cycling. If you ever watch the Tour de France, a lot of these athletes are spending lots of time in wind tunnels, trying to get into the perfect riding position so that they can go as fast as they can by expending the least amount of energy possible. And this is all studied using computational fluid mechanics. Another growing field is applications in energy. I've shown some figures here of that's renewable, but this is also in other kinds of energy applications where fluid is somehow involved with harnessing energy. A lot of times now, basically, it's coming down to computational models, which are all based on the fundamental concepts that we're going to be learning in this course. And then if you take Fluids 2, your fluid course. But basically, how can we design components to harness as much energy from a fluid, a moving fluid, to get that work out in a way that we can use it as possible. I noticed that George has his hand up. Do you have a question? No? Okay. So these are just examples of a wind turbine. We have a simulation of a dam, so maybe it's not just in energy, but if you want to model what might happen if something goes wrong, if you have a dam that ruptures, how can you predict what that flood path is going to be for anything that would be downstream to try and mitigate any risk? And then below that is a tidal wave energy capture device that was developed and I think tested in the Bay of Fundy off of the coast of Nova Scotia. So if we zoom out a bit and we try to think of really, really large systems and really complex problems, we can even apply the concepts of fluid mechanics and fluid dynamics to applications in geophysics and environmental science. So a lot of the work that NASA does is understanding the currents in the ocean. And due to the Earth's rotation, these drive most of the weather patterns that we see on Earth. And for an example, if we understand these fluid patterns, we can predict different kinds of trends like cold fronts or maybe potential storm events, heat waves, things like that. So just as an example, an El Nino is a weather event that's caused by water in the Pacific near the equator being much warmer than usual. And if that water increases more than usual, what happens is the Pacific jet stream splits before it reaches the North American coast. And if you've ever been to Calgary during an El Nino, it could be January and 25 degrees out. And it just seems unusual, but because it's a phenomenon that's not too unusual for there, they're used to that. Now we have an understanding of what causes this, and through fluid mechanics simulations, we might be able to predict these things happening before they happen. Maybe this comes into play if we want to predict if there's going to be a massive frost event or a slow spring. We can tell farmers and anyone involved in agriculture how to manage their crops so that they don't have any damage due to frost or something like that. So those are basically applications of fluid mechanics. We've just got a few more slides on basically introducing what a fluid is and some fluid properties and the concept of continuum. So in the most simple sense, the difference between solid, liquid, and gas is a solid keeps its shape, a liquid takes the shape of its container, and the gas fills its container. And the main reason that I also want to highlight between a liquid and a solid, the reason a solid keeps its shape is because it can resist shear stress or applied shear loads. Liquids can't. So liquids will flow under any applied shear force. It won't give any resistance, and it will just take the shape of whatever container it's in. So that's the biggest difference. Solids resist shear loads. And liquids can't resist shear loads. So when we look at solids and we zoom right in down to the atomic scale, solids are different than liquids because their molecules and atoms are packed and arranged in a regular pattern, or not necessarily a regular pattern, but a fixed pattern. So whether it is a regular pattern like a metal or an irregular pattern like a glass or a ceramic, there are more or less those atoms are fixed in space. And these are because the atoms are close enough that they have large cohesive forces between them that hold them together. So there's not enough energy for those atoms to be far enough apart to flow freely around each other. They're kind of stuck in their position. And these forces prevent any sort of relative motion, except for maybe a slight vibration or some things that might take really long periods of time, like diffusion. And typically when we talk about solids, we talk about, we can look at phase diagrams for looking at the different arrangement of those atoms, and when a solid might change phase into a liquid. And usually that happens by either changing the temperature or the pressure. So in this little diagram is just an example, water, a phase diagram of pure water. And as you increase the temperature or decrease the pressure, the solid phase wants to go either to a liquid phase or a gas vapor phase. So like we said before, when a solid is subject to a load, it will not easily deform. And even with deformed load, it will continue to support the load. So after it deforms some amount, it's going to continue resisting that deformation. And there's little distinguishing feature of a solid that is can resist shear stress, like we just said, and a fluid cannot resist any shear stress. So for liquids, molecules are not bound by their lattice geometry. They can flow freely past each other. And that is because they're a higher energy state than a solid. But that being said, their molecular spacing is still definitely a constant. So that means that a liquid poured into a container is still going to take up the same volume as it did before it was poured into that container. The distance between the molecules in a liquid isn't really changing any significant amount. Likewise with solids. And it's very different than gases, whereas gases, the spacing between atoms is very highly dependent on pressure. With liquids, there's more or less a constant volume as a function of pressure. You can change the pressure, but it's not really going to change the density that much. We say more or less that they're incompressible. And then lastly, down here, like we said, they cannot resist shear loading. So we'll get into this in much more detail. But if we were to apply a force on the top plate in this figure down here, if this was a solid, we would have resistance to that before we'd actually see some deformation. Whereas with a liquid, that top plate will just move to the side, and there will be no resistance in the terms of static resistance. What we might see with the fluid is something called viscous resistance. So with a fluid, the resistance to shear load is a function of how fast something is deforming, not how much it's deforming. Lastly, gases are basically, the atoms are so far apart that the forces between them are really, really weak, and they travel freely past each other, and they tend to be, instead of attracted to each other like in liquids, they actually repulse each other because they're so far apart. Gases have no definite volume. Their volume entirely depends on pressure and temperature. If they were just released in a vacuum, they would just dissipate away from each other indefinitely. Like liquids, gases can't resist shear stress. And in general, we'll talk about this a bit more when we talk about gases, specifically atmospheric gases. There's lots of assumptions to be made about pressure and temperature and the properties of gases when we're talking about fluid flow, specifically flow of gases. So there's some separations or some there are some assumptions that we'll make about liquids that we cannot make about gases, and then same thing, there's some assumptions that we'll make about gases as we go through this course that we can't make about liquids, and this all comes down to basically their temperature and pressure and density dependency. So another state of matter that's not too well known is, we're not going to talk about this much in this course, but it is another state of matter, and that is plasma. So despite how important it is to us and life on Earth, we still don't know a lot about it. Like gases, plasma have no fixed shape or volume. They're less dense than solids or liquids, but they're different than ordinary gases because they're made up of atoms where most or all of the electrons have been stripped away. So it is just the nucleus of an atom. And these nuclei, because they have no electrons, become extremely charged. And so we have, imagine a supercharged gas type state. There's lots of development going into developing fusion energy reactors. This highly depends on understanding and controlling a plasma state of material. Also, if you ever looked at the sun, you've looked at plasma, or if you've ever seen electric spark, lightning, that is all plasma. So the last short section before we take a break is the concept of a continuum. So another fundamental assumption that we're going to be making in order to do all the analysis throughout this course and basically all fluid mechanics, we're going to consider a small unit volume, and the volume is going to be representative of the bulk material or properties. So how can we make that assumption, and how is this valid? So let's first consider just a small unit volume. And when I mean small, I mean, let's consider on the order of the interatomic spacing of the atoms in a fluid. One second, I'll just close my window. So if we consider a small volume where we might have just a few atoms in there, the density of that material inside that volume would be the mass of all of the atoms or molecules inside divided by the volume of that small unit volume. And since it's so small and on the order of the molecular size, and so if we move this volume around, maybe the density or material property here, then over here. All of these properties might be slightly different. So we can't really use this really small unit volume to do our analysis because it's not very useful. We'd have to do it at every single point, and atoms are so small that it's just too much to calculate. It's too much variability. So it's not really useful to us. So if we consider a larger unit volume, then we encapsulate more information. There's more molecules in there, so we have more information. And all of our measurements that we use on a larger unit volume would just be an average over the total number of molecules that are in that volume. So for example, we would consider the number of molecules leaving is approximately equal to the number of molecules entering. It might not be exactly that because we're dealing with maybe 10 to the power of 10 molecules. Like there's lots in this volume. But because that change is so small over the number of molecules that are in that space, we can consider the properties inside that volume to be constant. So a continuum takes in a large enough volume, or considers a volume that is large enough to represent the bulk behavior of a material. So a continuum is a volume large enough to approximate bulk, say, fluid behavior. So how big is this unit volume? Well, if we think of the smallest unit volume for we could define our unit volume as delta V. If we make this 10 to the minus 9 millimeters cubed, it's incredibly small. That volume still has, if we look at air, for example, that volume of air still has 3 times 10 to the 7 molecules. So that's still a significantly large number of molecules to define a constant volume anywhere within that that unit volume, or a constant density rather, anywhere inside the unit volume. So density is one of the material properties, can be considered a smoothly varying function in space if we apply this continuum concept and our unit volume is, sufficiently small to capture this size. So what happens if we change the size of our continuum, or a unit volume? So the limit definition of continuum fluid density. In A, we see a figure that's an element volume in a fluid region, continuum density. So these lines here represent constant density. So as we move through this figure, we're increasing our density. Okay, so if we have a volume element that's too small, then depending on where we choose to do our analysis, we're going to have a lot of variability. And we call this microscopic uncertainty. Basically, we're looking at a region of the fluid that's just too small. And as we increase that, we can kind of get to our sweet spot where we don't really have any uncertainty anymore. And we can represent our material as a continuum, and we can do differential analysis. We can integrate over large areas to find basically bulk material properties. So this is our sweet spot. And if we choose a volume that's too big, we could begin to introduce things like macroscopic uncertainty. That could be due to geometry or different material properties around this. So we don't need to worry about that. So basically, everything that we're going to be doing for this analysis is throughout this course is we're assuming that we're dealing with, for any differential analysis, a volume that can be approximated as representative of the material properties, and it is part of a continuum. The properties continuously change as we move through a material. There's no erratic change. It's not a sudden step in pressure, temperature, and so on. So lastly, where does this kind of all fit in? There's lots of branches of fluid mechanics. I don't even think these are all of them. These are just some that I'm aware of. So this course is basically going to talk about incompressible flow, constant density, hydrodynamics, hydraulics, dynamic pressure. I didn't include this. We actually are going to cover some compressible flow, but most of what we're doing is going to be incompressible flow. There's also stratified flow, and that is where you have flow of multi-layered fluids. So if we think of the atmosphere, each layer of atmosphere has slightly different behaviors due to changes in temperatures or air currents or cloud formations, things like that. So if you're doing studies of layered fluids, that would be stratified flow, and that's more or less its own field. If we zoom out even more, your flow of fluids around the entire planet, that would be a rotating flow, and you need to consider Coriolis. So that would be like a geophysical application. And then finally, there's a lot of environmental fluid mechanics. I wrote it in as environmental, but if we look at surface waves, so we wanted to predict tidal waves, things like that, or tsunami waves, or just wake coming off of ships, internal waves, so that would be sound waves, acoustics, mixing and heat transfer, so how a fluid flows when it changes temperature, if we want to design better heat sinks or fans, sediment transport, if you're looking at erosion into river basins and trying to track the flow of that erosion material to river deltas or to oceans. All of these tie back in mechanics and the behavior of fluids. So there's lots you can do with fluids. This is just sort of a small little snapshot, and we're just going to be doing in this course a small of this small snapshot. So with that, we'll take a break. It's not the end of this lecture, but let's just say a 10-minute break, and then we'll come back and we'll go into fluid properties, and we'll start that and see how far we can get. Maybe we'll take another break after another hour.